So we're looking to find z bar, which is the conjugate of z. So the important thing to consider is the real number stays the same and the imaginary component changes, so 1 plus 2i. W to the negative 1 actually means 1 over w, which in this case is 1 over 2 plus 5i. However, we can never leave that in that form, so you need to cross multiply top and bottom by the conjugate, 2 minus 5i. So we're going to get 2 minus 5i. And remember, 2 squared and 5 squared is 4, and 25 is 29. Next one, simple middle algebra. 3 times negative 2i plus 1 minus 4 times 2 plus 5i, negative 6i plus 3 minus 8 minus 20i. So we end up with negative 5 minus 26i. Now, Cartesian form, we wish to find w over z, so that is root 3 minus I over negative 1 plus 2i. Again, cannot have a complex denominator, so we multiply by negative 1 minus 2i, negative 1 minus 2i. Expanding that, we get negative root 3 minus 2 root 3i plus I plus 2i squared, all over square negative 1, so it's 1, and 2, so 2 squared, which is 4, gives us 5. Calculating, you've got I squared, which is negative 1, so that becomes minus 2, so we have negative root 3 minus 2 as the real component, and then you've got minus 2 root 3i plus I all over 5. W squared and z cubed. Let's first of all work out w squared. So w squared is root 3 minus I all squared, which is 3 minus 2 root 3i plus I squared. I squared is negative 1, so this becomes 2 minus 2 root 3i. If we wish to find z cubed is negative 1 plus 2i cubed. Now we should know our perfect cube rules, so that is negative 1 cubed plus 3 times negative 1 squared times 2i plus 3 times negative 1 and 2i squared, and then 2i all cubed. So expanding that, you get negative 1, this becomes plus 6i. Now you get 2i all squared, so that's 4i squared, which is the same as negative 4, times negative 1, which is positive 4, times 3, so we get 12. And 2i all cubed is actually 8i cubed, which is negative 8i. So that means we've actually got 11 minus 2i. We now wish to multiply those two together, so you get 2 minus 2 root 3i multiplied by 11 minus 2i. If you follow that through, 22 minus 4i minus 22 root 3i and plus 4 root 3i squared. So we get 22 minus 4 root 3 as the real components, and then you can write negative 4 plus 22 root 3i. Powers, w5, z cubed, etc. Alright, since they're all in polar form, we will use things like Dumoir's theorem. So, w5 is root 2 to the power of 5. This is 5 times negative 5 pi on 6. So we'll simplify that while we're working with it. Root 2 to the power of 5 is root 2 by root 2, which is 2 by another 2, 4. So you should end up with 4 root 2. says negative 25 pi over 6. Now negative 25 over 6 is negative 4 and 1/6. So therefore negative 25 on 6 is the same as negative pi on 6. If we do z cubed, we get 1 on root 2 cubed, says 3 times 3 pi on 4. So 1 on root 2 all cubed is 1 over 2 root 2, and says 3 times 3 pi on 4 is 9 pi on 4, which is 2 1/4, so it's the same as pi over 4. Therefore, if you multiply them together, you get 4 root 2 times 1 on 2 root 2, and then you get negative pi on 6 plus pi on 4. 4 root 2 over 2 root 2 becomes 2, says negative pi on 6 is negative 2/12 plus 3/12 is pi on 12. Z to the negative 2 is actually 1 on root 2 to the power of negative 2, says 3 pi on 4 times negative 2. Okay, so 1 over root 2, if I squared that, I'd get a half, and then because it's negative, it flips over, so you get 2, says negative 3 pi over 2 by multiplying out the angle, which is the same as 2 says pi on 2, because negative 3 pi on 2 is travelling backwards to there. That's the same as pi on 2. We then wish to find out the cube root of w. Now, cube root of w, of course, is the same as writing w to the third. So we take our w value, which was root 2, we raise that to the power of a third, and then you have cis 1/3 multiplied by my angle, which was negative 5 pi on 6. So that becomes 2 to the 6th, cis negative 5 pi on 18, and that's all she wrote. Exact value of 2 cis 5 on 12. Well, first of all, recognizing what that means. That is 2 cos of 5 pi on 12 and 2 sine of 5 pi on 12 I. How do we get 5 pi on 12? We're going to have 2 cos 5 on 12 is 3 on 12 plus 2 on 12, which is pi on 4 plus pi on 6. And we have the same result for sine with an I next to it. So the addition formula for cos, that becomes cos of pi on 4, cos of pi on 6, minus sine of pi on 4, sine of pi on 6, plus 2 bracket sine of pi on 4, cos of pi on 6, plus cos of pi on 4, sine of pi on 6 I. So that gets you 2 outside of 1 on root 2 multiplied by root 3 on 2 minus 1 on root 2 multiplied by a half, and for the sine 1 on root 2 root 3 on 2 plus 1 on root 2 and a half I. So we actually get the same thing. You get root 3 minus 1 on root 2, because the 2's cancel through, plus root 3 plus 1 on root 2 I. So if you want to rationalise that, you get root 6 minus root 2 plus root 6 plus root 2 I all over root 2 multiplied by root 2, which is 2. Cube roots. First thing I would do, right, z cubed equals negative 1 plus I. That means that r cubed cis 3 theta is equal to, now we want to represent negative 1 plus I, so that's in the second quadrant, so the magnitude is root 2, 1 squared and 1 squared, cis, the angle 1 over 1 gives me a tan angle of pi on 4, so the base angle is pi on 4, but we are in the second quadrant, so it is 3 pi on 4. Common mistake that many people made. It's not negative pi on 4. Do not use the calculator. Work out the magnitude and then we'll get the corresponding quadrant. Therefore, r cubed is root 2. So r is 2 to the 6th, because it's the cube root of root 2. And 3 theta is 3 pi on 4. So theta is pi on 4. So z1 is 2 to the 6th cis pi on 4. z2, if you want to talk about the second root, is 2 to the 6th cis. Now, because we're dealing with cube roots, we want 3 equal angles, so we add 2 pi on 3 to pi on 4, so that's 8 on 12 and 3 on 12, which is 11 pi over 12. And the final one is 2 to the 6th cis. If you add another 8 to this, you get 19 on 12, which is the same as negative 5 pi on 12. Almost over. Fully factorise this given. So, what do we know? We know that z minus 3 plus I is a factor. We also know that z minus 3 minus I must be a factor because all coefficients are real and the conjugate root theorem applies. So this is the same as z minus 3 squared, because you notice it's a difference of squares, minus I squared, z squared, minus 6z, plus 9, plus 1. Therefore we've got z squared minus 6z plus 10 as our factor. So now I wish to write that multiplied by something else, getting me back to the original quartic. I need z squared to get me z4. I've got 10, I need to end up with a negative 20, so this must be minus 2. Now when you do this, you check out the highest next power. So if I multiply that through, I have 6z cubed, okay, in the bank. And I need to end up with negative 7. Right, so I've got currently, sorry, that's a mistake there. I have minus 6z cubed, and I need to end up with minus 7z cubed, so I need to take away another z. So we've got our two original factors, and now if I factorise z squared minus z minus 2, good old-fashioned cross method, 2 and 1, negative and positive. Okay, the nasty one. Everyone tried to do this the long-fashioned way. Let's break it back down to the basics. Alright, get the angle right. Let's start with the sketch. We're looking for our distance from 1 and our distance from negative 3, so that's the two pivotal points. And that total distance has to be 8. So what I do is find the midpoint first, and the midpoint between 1 and negative 3 is negative 1. Whatever value this is, I want to halve it. So we've got a total distance of 4. So if I move 4 units from here, that ends up being at 3, and if I move 4 units from here, that ends up being at negative 5. So they're going to be the outskirts of my ellipse. I also need to know that I have a point up here such that this distance and that distance are equal. This must be 4. Alright? So this is 2, this is 4. By Pythagoras you get 16 take away 4. This is the square root of 12. Our standard ellipse is in this form. I've got a translation here, so it's x plus 1 squared over a squared, which is like the radius in this direction, which is 4 units, so that becomes 16. Y squared, there's been no translation in the y-axis, over, that's my b, which is like my radius in the y direction, root 12, so if I square that, it's 12, and I get my equation equal to 1 all over. And last but not least, sketching cot graphs. The key to a cot graph is the asymptote. So the first asymptote for a standard cot function is 0, so I'm going to let my angle equal 0. Therefore x is pi on 6 solving. The next thing I need to know is my period. Now my period for this function is pi on 3. So label my axis, draw an asymptote at pi on 6. My next asymptote is pi on 3 later, so that would become pi on 2. My next asymptote is pi on 3 later, so that becomes 5 pi on 6. Notice this is now 1 6, 2 6, 3 6, 4 6, 5 6. Next skip is 6 6, so that becomes pi, which is the end of my domain. Going back, take off pi on 3, we get negative pi on 6. Take off another pi on 3, negative pi on 2. Extend that back, take it off again, negative 5 pi on 6. And we're going to have our little marker here at negative pi. So there's the domain we wanted. Tan graphs normally go like this. It's a cot graph, so we go like that. And we bisect the middle in each set of asymptotes. Okay. Now that means if I carry this pattern on, this must start up here and go down to here. Pi is in the domain, so I stop here. Come to the other side, I would have continued on from here, but I would have put a nice big fat open circle there because pi, negative pi, is not within my domain. Done.